Welcome to lecture 19 of MCS 471 on numerical analysis, and in particular today about numerical linear algebra, or even more specific about orthogonalization. So very briefly, the first part will be on alternative models. So far we have worked with polynomials, interpolating polynomials, and also briefly we looked into curves. But in many applications, the data is periodic, and there is also very often exponential growth or exponential decay. So periodic functions and exponentials are often then more appropriate to model the data. So in this first part, we will see how this can be modified. So the main goal of this lecture is to explain two methods to compute a QR factorization. We introduced the Gram-Schmidt orthogonalization method last time, but now we will investigate more on the stability and also define it properly, as in this course, that all algorithms are defined by Julia functions. So the second algorithm we then consider is the householder QR, which also has a geometric interpretation. We will end by listing two Julia functions that can be used to implement the householder QR. And by the way, the Julia implementation is most likely using a householder QR that can be seen from the shape of the orthogonal matrix Q that is returned. All right, let's then look at some applications fitting periodic data. So often when we make measurements, there is a seasonal fluctuation. There are very natural periodic phenomena that are observed. And then actually basis of cosines and sines they work specifically well. Now, as cosines are actually also polynomials, as we have seen with the Chebyshev polynomials. So there is also orthogonality that comes in this part here. But for fitting periodic data, one uses what is called a Fourier series. So in some sense, it should say it is a truncated Fourier series, because series go on forever. But one would hope that as the frequency, so k, determines the frequency, one hopes that the amplitudes with increasing frequencies die out. Now, importantly, so the textbook has one entire chapter on the fast Fourier transform. In this course, we do not cover this, but in a more application-oriented course, and actually we will most likely see this in 472, the fast Fourier transform is extremely important in practical applications. What matters also cost-wise is that actually it solves the interpolation problem in n log n time. So fast Fourier transform is just as fast as quicksort if you took a data structures or an algorithms course. So that's quasi-linear. So that's not linear, but very far from being quadratic. So in some sense, if the data sets are starting to get very, very large, you actually want to transition into an n log n method. Here is an experiment in Julia, how one could do signal processing. So what I want to point out that the FFT, the fastest Fourier transform in the West, is wrapped in Julia. And we can make a signal and then look at its fast Fourier transform. So the Fourier transform, what it does, it goes from the frequency domain, from the time domain to the frequency domain. So here we have the amplitude, so first plot. So this is the time plot, where you plot the amplitude versus time. And then we have the frequency plot, where you see the two spikes, and the spikes where they're not really coincidental. They are at the two places where we had a non-zero amplitude. So our test signal had amplitudes 2 and 5 and was running at frequencies that are corresponding to the two spikes here. So even if you are doing the interpolation with these cosines and sines, it will actually pick up the main frequencies. And one can do signal processing with this process. So assuming that the noise happens at very low frequencies, one can just threshold. So cut everything off below amplitude 1, which is already perhaps actually a bit too large, and you actually denoise the signal. All right, then. We often have exponential growth or exponential decay. And then one can also consider a linear fit here. This is very similar to the fitting with a line where we started with on the last lecture. We can go over through a logarithmic scale. So the model that we want is we want to find the exponent, the C2, but then also the constant C1. So we have two unknowns, and we see this phenomena here as evolution in time. Now, if it is exponential growth, then the numbers will getting larger and larger, and going over to a logarithmic scale is actually recommended. But if you do that, it seems to be also can be seen as a trick. What you actually now look for is a line, if the equation of a line. So I would then write this here as capital Y, so Y of t, and then we are looking for intercept. So the intercept is what we called our A naught, and our slope is the A1 from the previous lecture. So this is just doing a linear fit. So going to a logarithmic scale is recommended whenever you see very large numbers, but it's also here now very good for solving that problem. In general, one may also model things with a sequence of exponentials at various test frequencies. Here is an application. So in some sense, this is also a computer science course. Moore's law states that roughly every year, the number of transistors doubles. So sometimes if you look from 2000 to 2002, it doubles a little bit more. Sometimes it doubles a little bit less. I took this slide also to indicate in computer science the major transition that happened in going to multi-core. So 2006 was an important year here, where with the introduction of multi-core. So in a way, with multi-core computing, Moore's law is still holding up. There's also, by the way, exponential decay. If you look at this lecture, if you look at the frequency counts, The first lecture was watched more than 80 times, the second and third lecture about 20 times, and the lecture after were actually more in the single digits. So there is exponential growth, but there's also exponential decay. So the power law is a law that happens extremely frequently. So what is actually the power? So our exercise, first exercise, so on the previous slide I was using the exponential, but in the computer science world, the natural power is actually the base 2, and actually the natural logarithm is actually the 2 logarithm. So the first thing that you do with this data is that you take the 2 logarithm of these data, and I think that these numbers are naturally rounded. It might have been that they are actually powers of 2 or not, I don't know. I just copied over the data. But the point is, can you see that the slope still corresponds to Moore's law? So in a way, we started this new chapter last time with random data. So here is a linear fit on actual data. So in some sense, this exercise recaps what we did in the last lecture, but then more towards an application. All right, then let's go into now the main goal of the lecture. That's to explain some algorithms to compute a QR factorization. So last time we have seen that there is a geometrical interpretation of solving problems in the least square sense, that if you compute an orthogonal basis, or actually more specifically an orthonormal basis, because the columns of the matrix Q are normalized, then you solve the problem in the least square sense. And here this slide summarizes the Gram-Schmidt orthogonalization method, where the formulas are actually fairly straightforward. So you see, it's a column-oriented algorithm. So the main loop here runs over the columns of A. We have n rows, so there is another loop here. So that's the I loop. So that's the second loop. And then there is an inner loop. So here you see the computation of the inner products and also the normalization. And the cost of these inner products and the normalization is n for here the number of rows. I may still have to fix this. So typically we worked with M by N. So here we have an N by K matrix. So we obtain the Q from the orthogonal basis. So repeatedly subtracting the orthogonal projections onto the column space. And then if we collect these coefficients here, so in the algorithm, we will not evaluate the formulas as they are, but we will store those multiplier coefficients. And these inner products will actually correspond to the coefficients in the upper triangular matrix that we then solve. And that will lead to the QR decomposition. All right, one picture says more than 1,000 words, as the saying goes. So here is a vector calculus picture, where we have given 2 vectors. So they are in the plane, so they can be anywhere in space, but they span a plane. So actually we have already projected them into the plane. So the vectors A1 and A2 form a basis, so any vector can be decomposed in terms of A1 and A2, but actually that's not a good basis because the vectors are pointing both to the same direction, and we want an orthogonal, or actually an orthonormal basis. So the key operation to do this is to compute the projection of the vector of the second vector onto the first vector. So that's this vector v1, the first red vector, and then we subtract the projection to obtain the orthogonal complement. It's the complement to A1 of A2 in the opposite, in the perpendicular direction, not in the opposite direction, but in the perpendicular direction to A1. So then there is still one step, and that's the normalization. So the formulas in the previous slide do actually the operations, the normalization of A1 first, and then one works with Q1, and then one computes the projection, and then one normalizes again. So this is how you would interpret this geometrically, seeing that you decompose actually the new vector, the second vector, as the projection and the orthogonal complement. So there is a natural geometrical interpretation and also justification. So in a way, it's intuitively why the formulas work, but in a way you could proceed now with a proof by induction, why this algorithm, why the formulas are actually correct. All right, let's now look at the definition of the algorithm by means of a Julia function. So an advantage of Julia is that it's actually very straightforward to switch from 64-bit to big floats. So this is the big float. This is the 64-bit float version. If you just change the float 64 into big float, then actually you have a multi-precision version. This is kind of nice. So this function specifies, and then also each time how we are going to use this via the QR, so it returns Q and R, and each time, because this is a numerical analysis course, we will actually compute the residual of this factorization. So the factorization also has a residual, also has a backward error. So that's the difference from the original matrix with the product of the two factors. And then we check also the orthogonality. And here everything is still formulated with the NK formalism. All right, the algorithm can be very straightforwardly formulated in Julia, so there's actually no longer that much need for pseudocode. So except a little bit the ends that require space. But otherwise, it follows very much the formulas. So you see the outer loop, so we run over the columns, and then the inner loop does then this the repeated projections. So you can interpret this in inner loop as we take the jth vector, so the current column vector, and we project that vector onto all the currently computed columns already. So we compute this Rij. So this is the coefficient of the upper triangular matrix that is initialized by zeros. So then we subtract, and we then normalize to get the columns of the orthonormal basis. And then we have to do one more multiplication to get the element on the triangular matrix. All right, so this is the algorithm that essentially follows the formulas where we started with. Geometrically, mathematically, it's a correct algorithm. But what you will see here is that if you take matrices that are growing in size, is that the inner product of the last two vectors, so the matrix is orthogonal, but if you compute the inner product of the last two vectors, that actually should be zero, but it is not. So you will see that there is a growth that is there that is rather unfortunate. And with this experiment, you will observe that this algorithm, so there is a loss of orthogonality, is actually indicating that the classical Gram-Schmidt algorithm is a numerically unstable method. So it's just like we've seen LU factorization without row pivoting, this way of working is actually not numerically stable. So in doing this experiment, you run the function, copy this function in a cell in a Jupyter notebook. You run the function for the dimensions given here, and you will observe that the inner product of the last two vectors, as you select them from the output of Q, actually does increase. So that actually means that as the dimensions grow, this is not such a good algorithm anymore. But we have a fix. The fix is called the modified Gram-Schmidt method. So the conclusion of the previous exercise is that this is not a stable method. But the modified Gram-Schmidt method uses, so the idea, it's a little bit similar to Gauss-Seidel. If you have already an orthonormal basis for the first j-1 columns of A, you may as well also use it in your projection. So the difference here is that instead of keeping to use the original columns, you actually use the new columns. So actually we are using the vectors that have made orthogonal. So that is the main difference of the method. So in a way, this is a little bit geometrically. When I referred to the picture, I was saying that if you have a basis that looks like this, where in the plane where you have two vectors that are not so orthogonal to each other, your entire coordinate system, if you express any vector in terms of these two vectors, will actually also not really be that good. So that's a bit similar here. So we have a loss of orthogonality. And by the way, orthogonality also applies to polynomials. So we've seen that, I pointed out that the Chebyshev polynomials are a better basis than the power basis. And one can apply actually the Gram-Schmidt process to the monomial basis, 1x square, and then with the right inner product, you will actually find the Chebyshev polynomials back. So that's another way to get an orthogonal basis of a function space. All right, so here we have the modified Gram-Schmidt method now. No, I have written it as a pseudocode because the exercise, one of the exercises will be for you to modify the given Julia function for the classical Gram-Schmidt and to turn this into the modified Gram-Schmidt. All right. So this algorithm will actually use the queues. So you see that the gsar is being used each time. So we actually are, when we do our projection here, we are actually projecting using the Qs. So this algorithm is a column-oriented algorithm. So we have 2 times m times n square. So the n square comes from the 2 loops, and then we have the m. So here now I have switched the notation from n times k to m by n. So here now we have the modified Gram-Schmidt, so where actually the m comes from the inner products. So when we compute the inner product here and here, and also here, you can see the m coming in. The n square comes from the 2 outer loops. So this is a hand-waving justification. So the constant 2 is actually not really justified by that. But just to point out that with the LU factorization, so when m equals n, so if you compare this, so this would be 2 times n to the power 3. So it's a cubic algorithm, but it costs more than LU factorization. With LU factorization, we had the constant 2 over 3. So the Gram-Schmidt methods cost 3 times more than the LU factorization. All right, let us do a numerical example. So our running example again from last time. So this has been the time when the course was still being taught with paper and pencil. Let's follow through. So the square roots come in via the normalization, and we compute the coefficients via the inner products of the Q's with the A's. So we have a new vector coming in, we compute the R12, the projection, the magnitude of the projection, and we subtract that. So here we actually are using, so you can see we are using the normalized vector. So this is the modified Gram-Schmidt. This is not A1, but it is Q1 already. And then we find the last normalization. So you can verify again that these 2 vectors are perpendicular to each other, and we find coefficients in our upper triangular matrix. And everything works out fine again. So with the modified Gram-Schmidt method, we have a numerically stable algorithm to compute the QR factorization of a matrix. And this you might have seen in a linear algebra course. So in a way, the exercises that are happening in this lecture are probably familiar, except that we want to gain some familiarity with actual computation. So exercise 3 is good to run through the steps again, but now in a Julia session. Just tracing also, if you run the modified Gram-Schmidt method, and actually this is exercise 4, actually modify the Gram-Schmidt method, and then the first test would be to run actually exercise 3 on it. All right, that was our first method. So why now see a second method? Well, there are cases where the columns of the matrix is almost that they are almost linearly independent, linearly dependent from each other. So the modified Gram-Schmidt method is numerically stable in general, but it may not be that working that well when your matrix is close to being singular. We can derive an alternative method that uses orthogonality everywhere, also in the transformations. So here is how you can see this. So here is the introduction, a useful lemma. So if we have two vectors that are of the same norm, then we can compute an orthogonal basis just by subtracting and adding them to each other. So very convenient. So in some sense, intuitively, remember from the very early beginning when we introduced floating point arithmetic, is that we are going to lose a lot of significance if we are subtracting two numbers that are of the same magnitude. So in a way, the modified Gram-Schmidt method gets into trouble. Here what we are going to do is we're going to normalize the two vectors before we are going to do something with them. So in a way that's also to motivate why this lemma is here. So proving the lemma is very straightforward. It follows from the definition. And how can we use this? Well, we will use this to introduce many zeros. So one of the vectors will be parallel to one of the basis vectors, and the other vector will be any vector. So we will introduce zeros via a projection operator. So we can define a projection operator with any non-zero vector, preferably if the non-zero vector is actually normalized. So if you note that this is the norm, so if this is 1, then actually the operator is defined simply by multiplying the column Z with the row. Note that where you place the transpose is actually important. So vectors are typically column-wise. So the Z of t, so the transpose is a row vector. And the Z is a column vector. So P, the capital P, is a matrix. So this might look like a typo that we place the transpose now at the very end, but it is not. So the product of Z with its transpose is a matrix, and we can interpret any matrix as a map, and in particular here it's a projection operator. Why is that? Well, if you apply the matrix again, so this is also a very special matrix. If you multiply the matrix with itself, you get the original matrix again. So if you project something onto and then doing it again doesn't change anything. So this matrix is also symmetric. So you can work this out symbolically first on a 2 by 2 matrix, then on a 3 by 3, and then you will start seeing a pattern, or just with the formulas for the product. So flipping the index, whether you do the I times j or the j times I, doesn't really matter. All right, so now we get to a main definition of what is a householder, a reflector. So everything what we are doing still is very geometrical. So we project and we reflect. So the householder reflector is defined by a projector operator, and defined by this vector z, which is the difference of two unit vectors. Two unit vectors that prefer are not the same. So we have that the householder matrix is an orthogonal matrix. Notice again that we recognize the projection operator, and we will apply the projection operator here. So p square equals p, so the minus 4p cancels out with the plus 4p. So if we compute H transpose A, we have the identity matrix. So we have an orthogonal matrix. It's also a symmetric matrix, so this follows from the previous property. All right, so very fine now. So we know how to make orthogonal matrices. So in a way, this gives us a recipe for making somehow random orthogonal matrices just by one vector. We no longer need to do this QR on a random matrix. We can make random householder reflectors. What does this buy us? Well, here we are. We have what is called the reflector property. And perhaps I should not be so cruel and hold the geometric interpretation off. So here is the goal, what we want to do. So we want to make a matrix upper triangular. So this corresponds to taking any vector x. So x consists of two numbers. So I will indicate them here with stars. So the two coordinates, so the stars are both non-zero. And here we go to the vector y. And this is the vector star 0. So we are going from any vector to a vector that is parallel to one of the basis vectors, to the first basis vector. Now this is a projection onto the plane. Now this works for in any dimension. So we are actually by one matrix multiplication, and it is the multiplication with an orthogonal matrix. We are introducing many zeros in the matrix. So we call it the reflector because we draw here in dashed lines the bisector, and we are going, the black line actually maps the point of the vector to the endpoint of y. So the geometric interpretation should have come first, perhaps. Here is the algebraic justification. So actually what the reflector does, and this is regardless of whether y is now parallel to one of the directions in the basis or not. So for any two unit vectors, you can map one to the other by this reflector property. And this is worked out algebraically. So if you work out very carefully the product of H with the vector X and then work out the properties of the inner products, then you will see that things are starting to cancel out. So we also use very critically this last property here, that this factor, what is in the numerator, becomes 0 because what we used earlier, the very earlier lemma, the first lemma actually, that this vector z is perpendicular to the sum. All right. Let's play with this householder reflectors. How can we use this now to build a QR factorization? So in a way, this looks like a much more cumbersome method than the Gram-Schmidt method, but it works, and it's also very numerically stable because we are multiplying with orthogonal matrices. So here you see how the reduction happens. So we compute the norm of the vector, and then we find the norm the corresponding vector, which has zeros except in the first element. We define our projection operator. So here we have the projection operator defined from the vector z, and that then defines the householder reflector. And the property of the householder reflector is actually just to verify, because actually in practice you don't need to compute h times x, because we have already y. So we are going to use this projection operator to transform the rest of the matrix. All right, as an exercise, I could have asked to do this in Julia, but I did this exercise now myself. So here you see how you can verify. The square roots don't come out that nice, of course. It's a numerical exercise. We define z, and then we define the projection operator, where the transpose is here rather, so it should have been better given by the z. The prime also actually defines the transpose. We have our projection operator here, and then the final householder matrix. What is the cost of making this householder matrix? So there is an exercise still that we backtrack everything. So what is the cost for making one such reflector? Now the final object that you have is the entire matrix. So here we have the full representation of the matrix. And the matrix is a table of n square numbers. So the cost will actually also has to be n squared. But what is the constant? All right. So how does this algorithm work? So far we have only reduced one column. Well, here is how you can continue. So on a 3x2 matrix, you continue kind of recursively. So you actually continue with a smaller vector, with a vector of smaller size, and you do exactly the same thing again. And one accumulates the householder transformations. And the product of an orthogonal matrix is again an orthogonal matrix. So there's an exercise in the book that asks to prove this. Here, let's take that for, you can prove this by using the property of the inverse. So the inverse of a product. So one has if you have the inverse of A times B, then it is the inverse of times the inverse of A. So it's mainly following from that property. So it's an orthogonal matrix. So the orthogonality, so switching, so we have transformed, we have used so actually the product of all the orthogonal matrices is at the wrong side. What this actually shows here, but orthogonal matrices are very nice matrices to invert. So you can accumulate them at the opposite side. Here is how the algorithm then works. It's a column-oriented matrix. So one works on the first column. One then transforms actually the matrix further. So one can see the virtue is that one works column by column here. And the columns actually that you consider get smaller and smaller. All right, let's end now with two Julia functions. So the method is a little bit more complicated. One needs two functions. So one function to define the householder vector, and the householder vector, so the reflector matrix, this big H, is actually not stored as the big H. That's actually the main point here. So we return the matrix V, and this matrix V, so what actually I first underlined is where the computation happened. So in an exercise, you are asked to compute the total cost of this householder reflector matrix. And then I said, well, it's going to be square, right? Because you have an entire matrix. But here you see that the bulk of the work is actually the computation of an inner product. And the inner product, here I'm using the prime symbol, also from MATLAB, to do the transpose. So the sigma is actually where the main action happens. All the other computations are on scalars. So they don't. There are a lot of instructions here, but arithmetically, the bulk is where I place the arrow. So in practice, so the householder reflector is defined with a beta constant. That is defined here. I will not dwell on that. Let's now go to the main point. So the algorithm can be now, after we have the computation of the householder vector and the beta, can be defined very, very shortly. So the main point, so the bulk of this method is actually the printing, to allow you to see the progress of this algorithm. But here you see the update of R and the update of Q. Now this is a mathematical algorithm. If you are actually executing this, or if you would use this algorithm to determine the cost, then you would say, well, this is actually a very terrible algorithm, because the V times V transpose is actually a matrix. And here you actually do a lot of matrix-matrix multiplication. In this formulation, this is not a good formulation. So one should be careful with analyzing the cost with this. But with Julia, or also following the MATLAB notation, this algorithm is very shortly defined. All right, and I'm at the end now. So we have seen that the classical Gram-Schmidt method is a numerically unstable method. So, or at least that is what you will experience when you make the exercise. The modified Gram-Schmidt method makes an orthogonal basis, and as a byproduct gives the QR factorization, which requires substantially more work, 3 times more work than the LU factorization. The householder QR uses a reflector properties, and this actually should be applied when the matrix is actually nearly singular. So this is always numerically stable because we multiply with orthogonal matrices with these householder reflectors.